We're at the end here of week 14. So the end of the semester is upon us. So today we're going to talk about flux integrals, do a couple examples, getting the flux integrals set up. And then next week we'll look at Stokes' theorem and the divergence theorem, which will be generalizations of Green's theorem, which will give us different ways to evaluate flux integrals. So yesterday we talked about, what flux is, and this is sort of the constructive definition of flux. We're looking at how much of a field is getting through a surface, and by getting through, we're meaning getting through in the direction of the surface, so in the normal direction. And then we're multiplying that by the little element of surface area, and then we're adding all those little infinitesimal fluxes up to get us the flux across the whole surface. And then we look through and derive these formulas for flux, and this is sort of how we're going to proceed here today. Okay, welcome in, Tim. So example 14, let S be the portion of the plane x plus 2y plus 3z is 12, which lies in the first octant. Set up but do not evaluate a double integral to find the upward flux of this field across S. So they're using the word upward here. So up and down, that's typically a z direction. So if we look at one of these formulas here, to get the upward flux, we'd be using the upward normal. And so we're going to look at z equals f of xy, and we'll use this calculation. So basically what the goal is here, since we want the upward flux, we want to get z as a function of x and y. Then we can get our field as a function of x and y. We'll get our upward normal, minus fx minus fy positive 1. Then we will take the dot product. That'll be our integrand. And then we got to set up the double integral over the appropriate region. And since we're looking at z as a function of x and y, that region is going to be the projection of S into the xy plane. Right? So just like when we did the line integrals last week, or 2 weeks ago rather, the ultimate goal here is to get everything in terms of two variables. And so we've got, several steps to do here. So step number 1, let's look at our function, look at S here. X plus 2y plus 3z is 12. So we want z as a function of x and y. So what's that going to be? I solve that for z, what do I get? Yep, 12 minus x minus 2y all over 3, so that's the z. Now I have to get everything in terms of x and y, so I look at my field f. So f depends upon x, y, and z, according to the formula minus 2xz. xz y squared. And so if I want my field just as a function of x and y, I'm just going to substitute in the z as a function of x and y. So on this surface, the z coordinate is given by this expression in terms of x and y. So the field on the surface is going to be given by minus 2 times this expression, x times this expression, and then y squared. And we'll come back and simplify that later. But now we got the field in terms of x and y. Now I want to figure out what that normal vector is going to be. So the upward normal that we're using here is minus fx minus fy1. So z is f of xy. Once again, that's the 12 minus x minus 3y, excuse me, minus 2y over 3. So let's get the fx in here, and we'll figure out the fy. So in this particular case, what's the partial derivative of f with respect to x? Minus the third, good. And what's the partial derivative of f with respect to y? Minus 2/3. So my upward pointing normal I'm going to use here, it's the opposite of fx. So it'd be a positive third, opposite of fy, positive 2/3, and 1. So now we're going to calculate the integrand of the integral, because we're going to look at f dot n. So we'll see how much of that field is going in the normal direction, so passing through the surface. So f dot n. So once again, how do we do the dot product? We're going to multiply the corresponding components together and then add those up. So we've got the x components, the y components, and the z components. All right, so let's go through here. Let's add up the x components. So minus 2x times that. So this is going to be the x components. So minus 2x times 12 minus x minus 2y over 3 times a third plus, and now we'll do the y components. X, just x times 12 minus 2x minus 2y over 3 times the y component 2/3 plus z component y squared times 1. Any question on getting the components for the dot product? Now you see what's going to happen here? What do I have here? I've got minus 2x over 3 times that. Here I've got what? Positive 2x, or positive 2/3 times x, so positive 2x over 3 times that. So what's going to happen to these first two terms? Yeah, they'll completely cancel out, yeah. So these are gone. So that makes my integrand a little easier here. So the integrand then, f dot n up, is just going to be y squared. So once again, what this represents is how much of the field is getting through the surface, going directly through the surface at any given point x, y, z. And you notice it's just the square of the y value. So what's happening in the x and z directions are kind of mitigating each other. They're sort of canceling each other out. It's just what's going on in the y direction that seems to matter for this surface. Okay, so we know that our flux is going to be our double integral over r over f dot n up dA. And so to find our r, once again, since we're looking at z as a function of x and y, we're going to need to project s into the xy plane. So our plane, or what our s itself is a plane, x plus 2y plus 3z is 12. I'm just going to double check that. Yeah. All right. So if I go to sketch this, I've got an x-intercept of what? 12. Got a y-intercept of 6 and a z-intercept of 4. So here's my surface S sitting there in the first octant. So I got to project this into the xy plane. So I got my x-intercept, y-intercept are the same. So here's going to be the region R. It's the projection of S into the xy plane. And once again, what's a quick way to figure out what this is? That's going to be the what? Yeah, it's where the z equals 0 here. That's the xy trace. So x plus 2y is 12. So now I can set up the double integral. All right. So flux is going to be, we're going to have this double integral. The f dot n up, that worked out to be y squared. And now I got to pick an integration order here. Do you want to do dx dy or dy dx? Do dy dx, all right, it's a classic. If we do dy dx, then the x is the outermost variable of integration. So it's going to have constant bounds. We're chopping the x up between what two values? Zero and 12. And now for a fixed x, I got to figure out what the y runs between. So the y is going to start down here on the x-axis. That's y equals what? 0. And then for a fixed x, we're going to go from y equals 0, the bottom curve, to the top curve. And what's the top curve going to be? Y as a function of x. Yeah, 6 minus x over 2. And then at that point, you're off and running to get what the flux is equal to. So, once again, this should harken back to the work integrals and circulation integrals you did back in section 17.2. All right. Although this is a two-dimensional thing, so we need to get everything in terms of two variables. They want upward flux. Upward, up, and down is z. So we solve for z as a function of x and y. And then we use that to get the field in terms of just two variables, x and y. We get the upward pointing normal using our recipe that we talked about 2 days ago. We take the dot product to find how much of the stuff is actually going directly through the surface. That's going to be our integrand. And then to set up the integral, since we've got everything in terms of x and y, we project s into the xy plane, and then we set up the integral like we did in the last chapter. Okay. Any questions on any of the steps here? The key is keeping organized, right? Whoops, I went the wrong way. Yeah, exactly, Thomas. Yep. Once you've got z as f of x, y, everything has to be in terms of x's and y's. So you could do dy dx or dx dy, but it has to work in the xy plane. Now, if you put your integral together and it would be better in polar coordinates, once you get the integrand set up, you can convert to polar. We did one like that yesterday. But yeah. And we were tipped off about that because they wanted the upward flux. So upward is like the z. Does that answer your question? It's a good question. Okay, let S be the boundary of the solid bounded by z equal 4 minus x squared minus y squared and z equals 3. Set up but do not evaluate a sum of integrals that would find the outward flux of f across S, and the hint is to use polar coordinates. So let's talk about what's going on here. First, let's try to visualize this, what they're talking about. Z equals 4 minus x squared minus y squared. This is a popular character we've had already. What's this look like again? Yeah, it's a paraboloid, right? It's an upside down paraboloid. So it looks something like this. And now what's z equals 3? That's something we know. So let me mark that as the paraboloid. Yeah, that's a horizontal plane. So that's going to be z equals 3. Now what they want is they want the outward flux. So we're looking at this as the solid bounded by it. So let me ask you this. What direction would outward be coming this way? If you're coming through this boundary and you're going out of the region, are you going up or down? Yeah, they'd be going up. So this is going to be an upward flux out of here. And on the other hand, if you're coming out and crossing this surface, this would be what kind of flux? Down. All right? Now, flux is additive. So the outward flux is going to be, we can add it up. We can look at the upward flux across z equal 4 minus x squared minus y squared, and add to it the downward flux across z equals 3. Does that make sense or not, folks? All right, so let's start with the upward flux. Across z equal 4 minus x squared minus y squared. So we already have z as a function of x and y. So that part's already done for us. So now I want to get that field as a function of just x and y. So the field as given to us is 3x 2y z. So that's the field that they're given to us. So this is 3x, 2y, z. So if I want the field in terms of just x and y, I'm just going to sub in what z is when I have a z. So that's going to be 3x, 2y, 4 minus x squared minus y squared. So once again, we're looking at this field going across the surface. The field depends upon x, y, and z, but on that paraboloid, x, y, and z are related by the equation z is 4 minus x squared minus y squared. So on the surface S, or on the paraboloid, that's going to be the field. Now we're going to figure out the normal we want. The normal we want is the upward pointing normal. And thanks to the recipe we looked at, we got the other day, that's the upward pointing normal minus fx minus fy. 1. So the f of x, y here, 4 minus x squared minus y squared. So I need my partials. So my first partials, what's the partial of f with respect to x? Minus 2x, and likewise partial with respect to y, minus 2y. Plug that in. So I get the opposite of fx, which would give me the opposite of negative 2x, which is 2x. The opposite of fy, the opposite of negative 2y. And then it's upward pointing so that the z component is 1. And now I'll take f dot, the normal. So I'm going to look at the x component times the x component. The y component times the y component. The z component times the z component. And so when the dust settles, what do I get here, folks? Yes, I'd have 6x squared minus x squared give me a 5x squared. There's a 4x squared minus a y squared. That's a 3y squared plus 4. That's my integrand. So last thing is I got to set up the double integral, so I got to figure out what that region is. So my flux is going to be a double integral over r of f dot n up dA. I got to figure out what the r is. And since everything is in terms of x and y, I need to project what I'm working on into the xy plane. So remember, the solid I'm working with, it's bounded by z is 4 minus x squared minus y squared, and z equals 3. When I project that into the xy plane, right, how do I figure out what that region is going to be? What would I do? Yep, set those equations equal. So you see how all of the stuff that we did in the last chapter is coming to play. Like if we were trying to set up a double integral or triple integral to find the volume of this, you look at where these equations intersect. So you get x squared plus y squared is what here? So we got the good old unit circle. Okay. So here's going to be the region R. It's going to be, well, I guess technically it's the unit disk because we want everything inside as well. That means this is prime for polar coordinates. So let's go ahead and do that. So the flux integral in terms of x and y is the double integral over r of, what was it, 5x squared plus 3y squared plus 4 dA. Is that right? Okay. So we can go do this in polar. In polar, what's the area differential again? R d theta. So don't forget the extra r. Now, if I'm sweeping out the unit circle, what's the r running between? Yeah, constant bound 0 and 1. And for a fixed r, what's the theta running between? Constant bound 0 and 2 pi. Very good. So that's classic. And now we need to turn that into polar. Now, anytime you have an x squared plus a y squared, well, see, the 4 is going to be a 4. But anytime you have an x squared and a y squared, if you add those together, yeah, you're going to get an r squared. So what we can do is we can split this up. And we can think of this as 2x squared plus 3x squared plus y squared. Now, we don't have to do this now. We could use Pythagorean magic later, but I think it's easier to see it now. So this would be 2x squared. X is r cosine theta. So, yep, so that's exactly what you got. There's around 2r squared cosine squared theta. And then x squared plus y squared is r squared plus 4. And then you would multiply the r through. And you'd have 2r cubed cosine squared theta plus 3r cubed plus 4r dr d theta. And you could break that up into a sum of integrals, and then a couple of them you could split. Then you're on your way. Okay, so that would give you the upward flux. So this would be the upward flux across the top of the solid. So once again, upward indicates z is f of x, y. You want everything in terms of x and y. Get your field in terms of x and y. Get the normal vector in terms of x and y. The dot product then, how much of the force field is in the direction that you want. The region R is found by projecting the solid into the xy plane. Polar coordinates is the way to go. All right, any questions on setting this up? But hopefully you're taking time as you go through these problems. If you set them up step by step carefully, you're starting to appreciate how these problems are pulling together so many of the big ideas we've had in the course. Okay, now we need the downward flux across z equals 3. So the first step, z as a function of x and y, is already done. The f of x, y here is 3. So my field, once again, it's 3x2yz. As a function of x and y, on the plane z equals 3, it's going to be 3x 2yz, but z is always what? 3. Now for my normal vector, whoop, it's not up, but it's down. So the recipe we have for that is positive fx, positive fy, negative 1. But if f of xy is 3, fx and fy are both what? 0, 0, 0, negative 1. And now check out what happens. If I look at f dot n down, this falls out pretty quick, because the x component of n down and the y component of n down are both what? 0. I'm just going to pick up the z components, and 3 times negative 1 is what? Negative 3. So for my double integral here of r f dot n down dA, that would just be a double integral over r of minus 3 dA, which would be negative 3 times the what? Yeah, the area of r. Now, this r is the same r we had before, and this was the unit circle, right? Unit circle, unit disk. So what's gonna be this answer here? Yeah, so it's minus 3 pi. Now, the fact that the downward flux is minus 3 pi, what does that really tell you about this field? Yeah, it's going in. It's coming up through. So then to get the total flux, you would add those up. So this would be this was our upward flux, and then that would be the downward. You add them together to get the total. Any questions on setting these up? Once again, when you're given like equations with x, y, and z, you have to make a choice what 2 variables you use. Then you have to project things into the appropriate axes and things like that. But before we go on to the last example here, which is parametric, of course, parametric is nice because they give you the bounds. If we think about it, we can go back and we can, move letters around, and we'll do an example like this on next week. But like, let's say you had x. Let's see. I want to be consistent here. Did I call it the xg? Yeah. Or let's say let's say you had y as a function of x and z. Okay. Then remember, y in 3 dimensions, y is the left and right. Okay. So if you wanted like the right pointing normal to use, well, what would it be? Right is the positive y direction. You'd want a 1 there, and then you would have the negative partials gx minus gz there. The left pointing normal would be what then? We would want a negative 1, and then you'd have the gx here and the gz there. You follow? And then if you had x as a function of y and z, x is sort of out and back. Well, let's not do, let's do forward and back. So if you wanted the forward facing normal, what would it be? Well, that's the positive x direction, so you want the x here to be a positive 1. What would go into here then? And then the back. Yeah, minus hy and then minus hz. And then the back would be a minus 1 in the x component, and then hy, hz. Right? And we'll see this, like I said, we'll do an example next week where we use all these things. But just to kind of, that's for completeness here before we move on. All right, so our last example here, S is given by this. This is our cylinder. We had this, we talked about this character yesterday and the day before. This is our cylinder. Find the outward flux of this field across S. So in this particular case, we're already given everything. So what our goal is we need to get F as a function of U and V. Then we have to find the normal vector that we want that points out. And so this is either going to be RU cross RV or RV, or the opposite, I guess. Or RV cross RU, depending on how you want to do it. And then we'll take that dot product and then we'll take the double integral. Okay? All right, so let's take a look at this field. F of x, y, z is z, y, z. It doesn't depend on x at all. If I look at my parameterization R of u, v, on this surface, x, which we don't need, but x is given by 4 cosine u. Y is given by 4 sine of u. And z is given by v. So that means on this surface, I can use this parameterization to get F as a function of u and v. So what would the field be then as a function of u and v? Yep, v 4 sine u v. Everybody okay getting that to be our field? All right, now we got to look at the normal vector, which is RU cross RV, which we did this one yesterday. Was it yesterday or the day before? It was yesterday. Remember what we got? That was the magnitude of it. The vector itself was this. And when we graphed it, we noted that this was always pointing, out of the cylinder. All right. So that means that this is the normal vector we want to use. If we were looking at the flux into, if we wanted the flux into the cylinder, what would be your normal vector here? Yeah, we just take the minus of this. I'll just take the opposite. I won't write it out. So with parametrics, you sort of have to like test the point. We know that the magnitude is 4. That means that the vector never goes to 0. If the normal vector zeroed out, there's a chance it could then start pointing in the opposite direction we want it to. But since the magnitude here is 4, that's never going to happen. It's a smooth surface. It has a consistent orientation. Okay, so now we take F dot the n, and we do the dot product the way we've always done the dot product. We multiply the x components together. We multiply the y components together. We multiply the z components together. And we add all those up. So multiplying the x components together, we've got v times 4 cosine u. So 4v cosine u plus the y components. The y components are the same. I got 4 sine u, so that's going to give me what? 16 sine squared u. And then, yeah, the last is 0. I got 0 times whatever. 0 times v is 0. So there it is. So that's the f dot n. So this is going to be our integrand. And now we're going to set up the double integral over r f dot n dA. And what's nice about these parametrics is they give us the region here. We talked about this yesterday, actually. I think we found the surface area or something. I forget what we did. Surface integral. I'm sorry, not x and y. U's and v's. U's running from minus pi to pi. V is going from 0 to 5. So we got ourselves a rectangle here. So is the integration order really going to matter to us? Nope. Let's go alphabetically, du, dv. If we go du, dv, the u goes from where to where? Negative pi to pi. And then the v goes from 0 to 5. Okay? So it's easy to get lost in the weeds here. So I highly recommend you just sort of lay out your attack. Just go step by step. At this stage in the game, the way we're doing these surface integrals, you want to get everything in terms of 2 variables. If it's a parametric thing, that's great. It already gave it to you. If it's a function involving x, y, and z, you're going to have to make choices.